everybody. Okay, this is ICML 2024 oral presentation, and I'm first order of this paper, and Denoising and John Paisley are two advisor of me, and I come from South China University. South China University of Technology, and John is come from Columbia University. Okay, and also Denoising is come from South China University of Technology. Okay, this paper talk about sparse inducing points in deep Gaussian process. Okay, and our motivation is to use Denoising, diffusion, Variational inference method to enhance this model. Okay, so let's begin to talk about motivation and some background. And we all know in DGP, the DGP extends Gaussian process to multiple layers to capture hierarchical structures. So we all know DGP. DGP use these hierarchical structures to model the complex dynamic of a non-parametric Bayesian model, and as stacks some layers about Gaussian process models. The most crucial aspect is the selection of the inducing points. We all know inducing points is motivated to reduce computational burden, okay, and to accelerate the computation of DGP models. It's used inducing points as representations for whole data set to avoid the ON cubic computation to m square computations, where m is the number of inducing points. So and we also know this model can be solved by VI, especially Variational inference method. VI method aim to approximate the true posterior distribution by minimized scale, and this is well known. Okay, and we often construct evidence law bond of the marginal likelihood to solve this automations problem. Yeah, and we can make master album to get the optimal parameters of this VI model. Okay, and traditional methods include mean-field Gaussian VI and implicit postural VI. Okay, and we all know the limitation of this traditional method, where the SVI simplified assumptions fail to capture complexity complex dependency. Okay, because it's use a factor model of the variational distributions, and IPY use implicit posture, but it use adversary learning. This can lead to instability and significant bias. Okay, this is some limitations of traditional method. In this paper, we propose a method named DDVI. DDVI is inspired by recent inferential denoising diffusion models, and it uses denoising diffusion SDE and proposal similar to score matching. Okay, and we also increase mathematical theories of SDE and the bridge process trick. Okay, and we will explain these ideas later. And finally, we derive a rational lower bound, especially album, for the marginal likelihood function. Okay, and these are our attributions. We propose a novel parameterization approach for the posterior distribution of inducing points in GDPs, and we practice model infertility and specialized optimizations and training. And in our experiments, we empirically demonstrate effectiveness through extensive experiments and comparisons with baseline models. So let's talk about some details about our paper. First, we will introduce the Gaussian process. We all know that Gaussian process is a random function from Rd to R that maps the untraining input X to a set of noisy of the output Y. Okay, and we know the GP is a non-parametric Bayesian model. It models the data by a prior functional prior, and P where PF equals Gaussian, zero roaming, and KX text metric covariance, and K is the covariance corner function. Okay, and in sparse Gaussian process, MK teaches introduce inducing points. Z is a set including n inducing points, inducing m inducing points, where m is much smaller than n. So we use the inducing points to represent the whole data X, and the conditional distributions of f given u is also a Gaussian, because if f and u follows joint Gaussian, we can conclude f condition u is also a Gaussian, and and it avoids the computation of the k x, the inverse of the metric kxx, which has computation complexity of O n cubic. Okay. Next, we will discuss deep GP. DTP is DTPs are hierarchical models composed by stacking multi per output sparse Gaussian process, and each layer consists of independent random functions, where the output of one layer serves as input to the next. Especially the output FL of layer L is defined as equation 3. The equation for each FLD follows GP. Okay, and we can construct a joint Denoising model using equation 5, where P y fu equals these equations. Okay. You can use a chain to derive these equations because y is related to FL, capital L, and all layers have the same dependency in this model by equation 2, and PU is the prior. And in our papers, contrary to traditional method using DSVI or IPVI, we use the never parameterization method using Denoising diffusion method. Okay, and first we construct a Markov process. UTS plus 1 follows T UTS plus 1 given UTS. Okay, and this Markov process studied at P fix, which follows a simple Gaussian. And this Markov chain is constructed by a SDE, socket diffusion incursions 7 and 8. But it different from traditional DDPM method because U0 follows posterior distributions, complicating direct sampling. Okay, and we use incursion 9 to parametric this Markov chain. Okay, because incursion 6 is a numerical method to compute incursion net. Okay, and we also studied at P fix equals simple Gaussian. Okay, and we use the time revisor interpretations to generate sample at U capital T to get our approximation posterior samples. But the challenge we must face is traditional score matching technique is not feasible for our form order, because traditional score matching can sample from the P0, but in our VI method P0 is postural, complicating the direct sampling. So instead, we use approach minimizing KRP phi to P phi to P, uh, and the key challenge is to accurately computing gradient log P, due to the nonlinear drift function in the SDE. Therefore, we need to introduce bridge process trick to compute this care. Bridge process trick is a method to introduce the intermediate process. It is augment method to construct augment process UBRI, U bridge. It also introduces that U at P fix, which follows simple Gaussian, and it has the same dynamic as the forward processing equation 7. Okay. According to the classical SDE 0, we can obtain this involved incursions in incursion 12 and incursion 13. And we found that these questions are both ODE, So we can so if we have the initialized points, we can compute this involved process by this ODE, and we obtain equation 14. Equation 14 is and we finally get a Gaussian. Okay, this is the bridge process, the analytical solution of the bridge process. And we also we can also compute the reverse process and SDE by equation 15 initialized at PT. So the gradients also can be solved. Okay. Next we will compute the first term in equation 10 according to Grosnov 0. This is the famous in SDE 0. Okay. And for the second time, since P and P bridge have the same dynamic tau, so we can reduce this equation, this formula to a simple form. Okay, and we can also use the Bayesian rule to analyze this to solve this equation, and we got log py. In equation 20, we let log py to the left hand of the equation, and the rest to the right. Okay. The left to the rest term to the right, and we got equation 20. And finally, from that equation 20, greater than variational lower bound. Okay, and this is very similar to traditional VI method, but we use the fact that KL, the two process, the KL between two processes also is also positive. Okay, but in traditional VI we just use two different distributions. The KL of two distributions, but in this method we use the KL of two processes. Okay, and we finally we obtain a analytical solution of the marginal log py. So we can do the next regression or classification task. And also we have determined from this figure we can see that red points are our methods has got suta performance or the best performance in the baselines, and also we have the image data set classification task, and we have done unsupervised learning for data recovery task. Also we use the metric of RMC and NLL, and we also do large scale data set classification, and these are reference. Okay, and my presentation is has been done. So if you are interested in our ICML papers, you can if you are interested in our ICML paper, you can go to the OpenView website to search our data, to get the full paper and some more explanations of the special formula. Okay, okay, that's all. We are very glad to communicate with you. Thank you. Thank you, everyone.